It's only different from the others that we've had in that not only is momentum conserved, but also energy is conserved. And so you have a system of two equations with two unknowns. So let's see, it started out last time. It would just be a one-dimensional problem like this. I have one object collided with another object. I don't give you any final velocities, but because it's an elastic collision, you can still create that system of two equations where you have the initial, your first equation being that the initial momentum is equal to the final momentum here, and then your second equation being that the energy initial is equal to the energy final. Right, I wrote that here where you have the kinetic energy initial for the first particle, the kinetic energy initial for the second particle, and that's equal to the sum of the kinetic energies for the first and second particle in the final states, which is here, here, these two. I solved this. I'll try to make, if I give you something like this, I'll try to make the numbers as simple as possible. Like here, for example, I let one of the velocities be 0, and that gets rid of a term. But they're slightly more complicated than the other problems that we've worked. But here I solved this equation for V1F, and then I plugged this in up here for V1F squared. And then you can follow the algebra through. If you get it up to this point, if I give you such a problem, that'll be most of the credit. The algebra I just usually count a couple of points or so. So if you get the algebra mistake there, it's not a big issue. See, I'm going to put in some numbers here. I find it's a little easier to deal with. So I'm going to go from right here. I have a half of 1 kilogram. The velocity was 2 meters per second squared. And then that's going to equal, hey Chase, a half of 1 kilogram times 2 minus 2 V2F squared plus 1/2 of 2 V2F squared. And then I'm just solving now for V2F squared. It's going to look like this. 2 is equal to a half. If I expand this, it's 4 minus 8 V2F plus 4 V2F squared. That's just doing FOIL on that 2 minus 2 V2F plus V2F squared. And actually this isn't a quarter, this is a half here. Sorry. Here. And then I can distribute that half and combine like terms. And I get 2 equals 3 V2F squared minus 4 V2F plus 2. And this works out simply because these 2's cancel out on either side, so I'm left with a 0 here. And so I can solve for this. There are two possible solutions. One is that just everything is completely stationary and not moving at all. But I know that since I have a collision, that's not true. And the other is some non-zero velocity. I do that by factoring out a V2F minus 4. And then I solve. I can have V2F equals 0 will make that equation true, or I can have this equal to 0. So that's 3 V2F minus 4 equals 0, or V2F. The final velocity of that second particle is 4/3 meters per second. I'm not too concerned about the algebra part of that. I'm more concerned that you're able to set up the equations. But to get full credit, you'll need to go through the algebra. And I'll try to make it as simple as possible with the numbers. If you have something like this, you may or may not, I'm not sure. But you should be prepared for that. Alright, so that's the end of that chapter. Let's spend a little time just sort of reviewing what we've had in the chapters for the test on Wednesday. Your test will be similar to before, 15 multiple choice are maybe fewer, but I'll count 15 like I did last time. And then 4 to 6 free response. Got any questions about sort of the format of the exam?
Sorry, what is COM15?
What's that?
COM15.
15 multiple choice. Oh, so remember last time I gave you 13, but I counted it as 15. That means that I basically gave you two free questions. So you'll recall that. I might do that again. I tend not to do very well on the multiple choice, so so maybe if I had like ghost questions, ones that you can't see but you obviously get right, they'll be better. Okay? But to prepare for the multiple choice, go through the concept test and go through your notes. I've loaded the concept test on the website. They're also in the back of your book. You can use those to quiz yourself on it. Right. We will have class. I'll give the exam at 7:15, and then so you'll have an hour and a half or so. All right. So for the other parts, we've done a couple of different things. We've done work and energy, and then we've done momentum. So the work and energy, and I'll write this down in just a moment. We'll sort of go through it. But we being able to calculate work. Work is equal to the dot product or the scalar product of the force and the displacement. Make sure that you can do a dot product and you know what that means. Also make sure that you can just calculate the magnitude of the work. Remember the definition of a dot product is the magnitude of both vectors multiplied, f times d, times the cosine of the angle between them. So you should be able to do both the dot product and the just the magnitude of the work, or just the taking the magnitude of the vectors and then angle with respect to one another. And then also the work due to a position varying force. A good example of that is a spring, right? And we actually calculated the energy from doing the integral of f dx and doing the integral of kx dx, and that's 1/2 kx squared. Also be able to calculate the work due to a force that is changing with some other function. We did a couple of examples in that, and you have some in your homework. So where I give you a function that says the force here is equal to x or y cubed or squared or however it may vary, and then be able to calculate the force be able to calculate the work as that force acts over a certain displacement. And we did that. It was work was the integral of f dx. And then conservation of energy. When you're dealing with conservative forces, by the way, know what conservative and non-conservative forces are. Conservative conserve energy, non-conservative do not conserve energy. What's an example of a conservative force? A field force, a force that does not require contact is a conservative force. Gravity and electric forces are good examples of that. And then non-conservative don't conserve energy. Friction is a great example. So conservation of energy, something like the roller coaster type problem that we did, where you have an object that's moving up and down and up and down, and being able to find its velocity within that gravitational density. You will have a problem like that for sure. And then after that, we did power. That might just be sort of thrown in as an extra part at the end of one. So if you do work over a certain amount of time, how much power have you done? It's just work or energy divided by time. And they're in the units, but out of the watts. And then in chapter 6 was momentum. It was fairly short, but there were a few things. We had impulse and momentum. That is that force is equal to your change in momentum over your change in time. And so you can calculate the force if you know how the velocity of an object has changed, or how its mass is, how its momentum changes. That's like the car running into the wall, or you have a couple homework problems. I think there's one like a catcher catches a baseball. What is the force implied? You know that you're dealing with that type of problem if you're just dealing with one object that sort of bounces off of another object. Right, that like it runs into something that's stationary, like a wall or a catcher. And then conservation of momentum. If you have one of those, very likely that you will. That's a collision of two particles. You'll just have two particles, but they'll likely be moving in two dimensions. Right? So that means you'll have to. We did a couple examples, but you'll need to basically just keep your vectors in INJ notation. If they're not in INJ notation, then you need to put them in INJ notation. That means take the X and Y components. You have to clear what I mean by that? Like if I give you a vector velocity 10 meters per second at 30 degrees, then you'll need to express that in INJ notation. Yes? Okay. So 2D collisions, you need to know elastic versus inelastic collisions. You'll probably see a multiple choice question like that. Elastic conserve what and what? Yeah, they conserve both. Elastic collisions. I was thinking like elastic collisions are really bouncy, right? Like elastic. And in really bouncy collisions, you conserve energy and momentum because you don't lose any energy when they bounce off of one another. Whereas inelastic collisions, which aren't really bouncy, like a beanbag, for example, or cars crashing into one another, those aren't real bouncy collisions. They're inelastic, and they do not conserve energy. They only conserve momentum. But all collisions conserve momentum. Every collision that has ever occurred conserves momentum. And then, so within elastic collisions, like this example that we just worked, when we started last time and finished up this time, you could have one of those, maybe, maybe not, I'm not sure. There's sort of a lot of different topics that are coming together, so it's depends on the scene. All right? Y'all know, what do you feel weakest on? And we could spend some time now working through some problems that are similar to ones that we've done already. Well, what would that be? What are the weakest things that you feel? Just take a couple minutes. Maybe the position varying force, maybe an energy problem related to that in some way. Maybe your 2D momentum collisions. I'm giving my other classes the questions. Would y'all like to have it as well? It doesn't have everything on it that y'all have, but like it doesn't have the dot product on there because they don't do that. But that's really the only thing that is missing. Y'all would like this? Okay, I'll give it to you. Don't be lulled into thinking it'll help a whole lot. It might help you some, but you generally need to know the equations to be able to do them well. So, but I'll send this out to you in an email.
But we need to know that JJ equals 1 and KK equals 1.
Yeah, for your dot products, yeah, you need to know how to do the dot products. In order to do that, yeah, you have to know that two vectors in the same direction have a dot product equal to 1, or two unit vectors rather in the same direction. And two orthogonal vectors at 90 degrees, their dot product is equal to 0. You can know that because the cosine of 0 is 1 and the cosine of 90 is 0.
Can we go over like a problem, like we had chapter 5 where we had something we had to integrate within the problem?
Yeah, I understand what you're saying. Yeah, let's try to do one that's different from what we've had. We went camping this weekend. Okay. We had a good time. Yeah, okay. I'll show you some pictures later if I finish up. Alright, so I think you had a homework problem similar to this. Was that the ramp? Or was it just a flat thing? Oh yeah. Let me try to think of a different one. I think. So will this work? No, that might get too complicated. Let's do this one. We might have done one similar to this. No, let's just do a vertical one. So let's just say that we have an object here. Alright, and it's traveling with a velocity equal to, say, 10 meters per second. Alright, and right here, the frictional force, there is no force acting on this. So it's traveling, and as long as there are no forces acting on it, it's going to go on forever. Alright, let's say that this is a 2 kilogram object. And then it comes over to this place over here where I have some force acting on it. Alright, I don't know what the force is. It's not friction, it's something else. That force, this is x equals 0, this is x. That force is equal to, let's say, negative 4x squared. So as the object continues moving on, that force increases. So as x increases, the force increases. And notice that the force is negative. That means that the force, which is in the x direction, is going to be in the negative x direction. So it's going to oppose the direction of motion. And the problem is simple. I just want to know how far does the object go until it stops. So this force does a certain amount of work. That work is equal to the integral of f dx, which is equal to the integral of negative 4x squared dx, which is equal to negative 4x cubed over 3. Remember, I do x to the n, the integral of that is x to the n plus 1 divided by n plus 1. And then I have to evaluate this from x initial to x final. Now x initial is equal to 0, and x final, I don't know what that is. I want to find out what that is. So my total work that's done is equal to negative 4 x final cubed divided by 3 minus negative 4 x initial cubed divided by 3. But since x initial is 0, this latter term just goes away completely. So I'm just left with that first term. So that amount of work is being pulled away from the object, and I want to set that amount of work equal to the total kinetic energy. So in the beginning, this object has a kinetic energy, which is equal to 1/2 mv squared. That's going to equal 1/2 of 2 kilograms, that's its mass, times v, which is 10 meters per second squared. So that's 100 joules. So then we would take this 100 joules and set it equal to the work that's done. Or actually, the way we're going to look at this is we'll say at the end, after the object stops moving, it will have an energy equal to the kinetic energy plus the work, and that total energy will equal 0. So that's how we deal with that negative sign. So then we have 100 plus negative 4x f cubed divided by 3 equals 0. And then we would solve that for xf. So that is xf cubed equals 3/4 of 100, or xf equals, yeah, cube root of 75, which is, what is that, 5? Yep. No, that's not right. Whatever that is. Is it 4 times 4 is 16? 3 point something. 4.2. 4.2. All right. So that means that this object traveling along will travel for 4.2 meters along that place where that force is acting. You could do a different problem. Can I go down from here? You might have had a homework problem. Does this get too... Did y'all have a homework? Oh, let me go see. I think I might have taken it off because... Oh, this is the wrong chapter. Computer's locked up here. Yeah. was looking at this one. Could I do that one? I think if your x changes, you can't do a function for x. I don't think I'd do a 2D problem. Okay, but you could see a problem like this where you just have friction in play, where you have to calculate the work that's done by friction, and in this case, the work done by friction would be equal to just, you know, the force due to friction times the distance along the frictional surface. Then you don't have to integrate, you're just taking the product of those two. Alright, you'll definitely have one of these type problems, so like in the part A of this problem, where it's like the roller coaster type problem, where you're dealing with potential and kinetic energy.
When you deal with it like that, one of each is just equal to 0, and you set them equal, right?
What now, Courtney?
It's like where you set the potential energy at the top equal to the kinetic energy at the bottom.
If that's the case, yeah. So, well, like for example, here in this problem, this object was stationary at this point, so its kinetic energy was equal to 0, but its potential energy was equal to mgh, right? At the bottom over here, the potential energy equals 0, and the kinetic energy equals 1/2 mv squared, but the total energy is still going to be the same. And then here, the kinetic energy and the potential energy are both non-zero. So mgh and 1/2 mv squared. But the sum of those energies is going to be the same all the way throughout. We worked several problems like that in class. You'll see one of those for sure. All right. What else? Are y'all okay with the collisions? 2D collisions? Those are pretty simple. Well, I don't say they're simple, but they're fairly straightforward. So remember, you just want to keep your I and J and K notations separate. So you could have 3 dimensions actually. So like for example, let's say we had a 2I plus 2J problem, an object 1 kilogram colliding with one that is 2 kilograms, let's say negative 1I minus 1J. That's the initial state. And then let's say that they stick together. We might have done one like this, where you have a 3 kilogram object, and I ask what is its velocity. I think we did one like this. If they don't stick together, then I would give you the velocity for one of the other objects. Okay, and then I can solve for the velocity, the final velocity of that object. So I just say pi equals pf. Keeping it in vector notation, that's going to be 2I plus 2J, 1 kilogram, plus 2 times negative 1I minus 1, oh, it's going to be 0 actually, is equal to 3 kilograms times P final. But here actually these go away. So I'll probably give you some different numbers so your final momentum would be 0. But then you would solve for PF. Okay? Y'all good on that? I think you're okay, right, with that? Need to know how to do dot products. How are y'all on dot products? Done several. Yeah, sure. Find a blank page here. See, not this problem, but it could be something as simple as I'll just give you a force and I give you a displacement, kind of like we did in class, and ask you to find the work that's done, and then maybe also the power that's done. I've done that in the past on tests. I won't count a whole lot of points, 5 or 10 points, but a problem that you can do quickly and just hopefully be done with it. So if I tell you, say that the force is equal to 3I newtons, and it acts over a displacement of, actually let's do 3I plus 2J, and it acts over a displacement of 2I minus 3J meters. Then I want to know what is the work done by these. That's going to be F dot D, which is 3I plus 2J, dotted with 2I minus 3J. And remember, with dot products, you only take like terms. So I multiply these and I multiply these. That gives me 6. I lose the I because I dot I equals 1. Minus 6. And this is 0 too. Goodness. Just pulling zeros. So here I say I dot I equals 1. And that's why those I terms go away. The result of a dot product is a scalar value. It's also called a scalar product. J dot J is also equal to 1. If I pull that out and do the full FOIL, first, outer, inner, last, it's your J dot I terms and your I dot J terms go to 0 because the definition of a dot product, F dot D, is FD cosine theta, and the cosine of 0 is 1, but the cosine of 90 is 0. So the dot product for orthogonal or perpendicular vectors is always 0. So that's why you just multiply out the like terms. Could see just a simple dot product. And hopefully that would be an easy 10 points for you. Alright. What else? Any other questions? We're going to go on to chapter 7 unless you'll have some more questions. I'm okay spending more time on this, but...
Did you do the roller coaster?
Yeah. Hopefully this is an easy test. I want good grades on this, okay? So, but not easy, but a doable test, a test that we can do well on. So I'd love to see like an 80 average in the class. And don't forget drop day is this week too. So if you're thinking about dropping, I mean, obviously you're going to take the test or you wouldn't be here. But don't consider dropping until you've taken the test and also that you've spoken to me, because even if you think it's going really poorly, it might not be that bad. So make sure you don't drop before you come talk to me. Yeah, so let's say we have something like this. Let's say that we have an object up here, has a mass of 2 kilograms. And let's say that it has a velocity, an initial velocity equal to 1 meter per second. All right, and that this height at this point is 5 meters. Let's say that this height is 2 meters, and this side over here keeps going up. And I would ask you, for example, several things. I would ask you, what is the speed here? What is the speed here? And how high does this guy go up before he stops? So what is this height when v equals 0? It would probably look a lot like this, actually, asking you those questions. You would need to recognize that at the beginning over here that he has kinetic energy and he has potential energy. Over here, he only has kinetic energy. At this third point, he has kinetic energy and potential energy. And at this last point, he only has potential energy. And then, since I know both the kinetic energy and potential energy here, I can set them equal to the total energy at all the other places. So it would look something like this. The total energy at the beginning would be 1/2 mv squared plus mgh, where h equals 5 meters. And then that would equal to 1/2 mv2 squared. I'll call this number 1, this number 2, number 3, and number 4, just to keep my numbers straight. So this is v1 squared and h1. Alright, so I'm solving for that velocity at point 2. Notice that my masses here cancel. 1, 2, 3, they all go away. And then I just go about solving for v2. So I have 1/2 of 1 squared plus 10 times 5 equals 1/2 of v2 squared. It's 50.5. There's 2, that's 101. Square root of 101, which is approximately 10, is equal to V2. So that would be your first answer. V2, the velocity at that lowest point, is equal to approximately 10, square root of 101. Right? And then at this second point, it would be very similar, but a little bit different. I would say that the total energy, which is 1/2 mv1 squared plus mgh1, or now that you know the velocity here, you could say just 1/2 mv2 squared, and that might make your math a little easier, is equal to 1/2 mv3 squared plus mgh3. Masses all cancel. 2, 3, 4. I just have one unknown in this equation. That's my v3, so I solve for it. I'm going to put in some numbers here. This is 1/2 of 1 squared plus 50 minus 20. The minus 20 came from here. This is equal to 20, so I subtracted 20 from both sides. That's 30.5. Square root of 60.5 is V3. So whatever that is, 7 point something.
Where is it in this 20%?
This G times H3 is equal to 20 because H3 equals 2 meters, and so 10 times 2 is 20. And then finally, part 4, I do the same thing. Although in that part, it only has potential energy, so it goes up and it stops at some point. Now, if this velocity had been 0, that distance would be what? It would be exactly the same. It would stop at the same height that it started. But because it has a velocity that's non-zero, it continues going up. So here I solve for M, or I solve for H4. No, it wasn't. What was it? 1 squared, excuse me. So that is 0.5, 50.5. 5.05 meters. So it goes up an extra 5 centimeters. Something like that. It'll have several parts. It'll be something very, very similar to that.
And unless you tell us the object starts off at rest, it does not. I mean, it doesn't have kinetic energy.
That's right. If it's at rest, it has no kinetic energy. Yeah. It does have potential energy, yeah. Why? Why does it? Because potential energy, remember, is equal to mgh, and here h is not 0. Better question asks is why doesn't it have potential energy down here? And that's because h equals 0, so potential energy equals 0. So anytime your y position is 0, that's when your potential energy is 0. Anytime your velocity is 0, that means your kinetic energy is 0. All right, hopefully that's an easy 15 points on the test. I think that'll be an easy 15 points, right? Just be careful with your algebra because you want to get all the points. It's a lot easier if I just go through them like, oh, I did that exactly right, and then it's minus 0. I prefer minus 0 to minus 3 or 4. What derivations did we do? No. Did I say this one? No, I just wondered. Okay. But I mean, that just comes about from the integration of a position varying force. Yeah, basically.
I was going over the homework yesterday, and for number 6 on the chapter 5 homework, I was confused. Like when work was being calculated, you had the distance as 60 cosine of 0, and then just like wondering how.
Hold on, let me. Let me erase all this. I wrote on this page. Give me just a second. I did that on a page when I shouldn't have. Okay, which chapter was it, Courtney?
Chapter 5, number 6.
Chapter 5? Okay, can you repeat your question?
We were calculating work, and the distance, like you had it as 60 cosine of 0, and I was wondering how you got cosine of 0.
Oh, because you have that angle of 30 degrees. Is that what you're wondering? Yeah. So the thing here is that I have this force that's pulling this guy up. Okay, so the force is in that direction. Now, you had to figure out what that force was, right? And so in order to find out that force, you had to say, well, my force weight is in this direction, and that weight has an x component of Fw cosine of 30 and a y component of Fw sine of 30. So that's why you needed that angle of 30 degrees in order to find out what must this force be. So this force must equal Fw cosine 30. All right. However, when we get to work, our work is equal to Fd cosine theta. Oh yes, I'm sorry. So F cosine 30 or sine of 60. I'll write it like that. So if this angle is 30 degrees, this is sine of 60, and this is cosine of 60. You with me? With me? Okay, so I know that this force right here has to be equal to Fw sine of 60, right? However, this angle right here is the angle between the force and the displacement. But in this case, our force and our displacement are in the same direction. So in this case, we don't have a situation that looks like this. Instead, our situation looks like force and displacement are in the same direction, and for them, the angle is equal to 0 degrees. Are you sure? That angle is the angle between your two vectors, f and d, of your dot product. And if they're in the same direction as they are in this case, it's equal to 0.
I just didn't know that it was the angle between the force and the
Okay. Yeah, I understand. All right. What else? It's good to go through that homework. Sometimes I just go through the homework and I can pull a question. So hopefully, again, that's an easy 10, 15, 20 points. All right. Any other questions? All right. We only have about 10 more minutes, so I think we'll just skip off on Chapter 7, and we'll pick that up on Friday. We're not going to skip Chapter 7, but we'll pick that up on Friday. But remember, come in at 7:15. If you have more questions, I'm around, so if y'all want to sit down for a little bit, I have about 15 minutes before I have to go. But 7:15, sort of same format as before. Not going to do a rework this time, okay, so don't depend upon that. That's like the first rework I've done in like 3 or 4 years. So, all right. Have a good day. Oh, and you will have an equation sheet. It'll look like this. I'll send it out to you on email just so you know what's on it. But the dot products are not on here. as well as the interval of the FDX isn't on there. Those are the only two things not on there.